Hello friends, today we are going to solve again Kani's method. This is continuation of my previous video in which I solved problem 1 and now we'll solve problem 2. This problem is distinct from problem 1 as one end support is fixed and the other end support is a pin jointed, that is it is in our case a roller. Okay. So since this is a pin jointed and thus there is some changes while doing the iteration process in the Carneys box, that is step 3. Okay, so step 1 and 2 are almost similar to the previous problem, but still we'll go through them. Okay, step 1 is finding fixed end moments. If you have already seen my previous video, you might have actually seen what are fixed end moments, but if you have not, this is a tabulated form of fixed end moments that I have shown it here, and you can either pause your video and look at all the fixed end moments, memorize them or write them. So the fixed end moments that we will require is, for this case, there is a point load acting at the center, a point load acting at a distance a, and a UDL spanning throughout the span. Okay, so these are my fixed end moments that are required. Now we will start with the fixed end moments. First is MFAB, which is equal to minus WL square by 12, and where W is 60, L is 4, and we get MFAB as minus 80. So fixed end moment here is minus 80. Why is it minus? Because since my UDL tries to bend the beam like this, it is bending the beam in sagging manner. This is a sagging manner, and there's a resistive anti-clockwise moment that is formed at joint A. That is the reason it is negative, because as per my convention I am taking negative as anti-clockwise. Okay, MFBA, fixed moment at this intermediate support B, is equal to WL square by 12, and it's positive, so it is plus 80. MFBC, MFBC is equal to minus WAB square by L square. You can either use this formula or you can also use the formula as WL by 8, since this load is acting at the center of the span, that is 2 meter. It is dividing it into equal halves, 2 meter, 2 meter. But I prefer to use this formula as it is a generalized formula. Thus MFBC is equal to minus of W is 80, A is 2, B is again 2, and L is 4. So we get as minus 40 kilonewton meter. And MFCB is WA square B by L square, where again W is 80, A is 2, B is 2, and L is 4. So we get plus 40 kilonewton meter. Signs being the same as I explained to you for this concept, and that is anti-clockwise negative and clockwise positive. Okay, and MFCD, fixed end moment at CD, is minus WAB square by L square, where W is 45, A is 1, B is 2, and L is 3, the total length of the member CD. We get it as minus 20 kilonewton meter. And MFDC is equal to WA square B by L square, where W is 45, A is 1, B is 2, and L is 3, and it is plus 10 kilonewton meter. So the step 1 of fixed end moments is done. We'll now see step 2, that is rotation factors. Rotation factors are basically found for those joints which are intermediate. So here the intermediate joints are B and C, which connect to two members BA and BC. Joint B is connecting to BA and BC, and joint C is connecting to CB and CD. Alright, so our first column for finding rotation factor is writing down the joints, intermediate joints, which are B and C. Second is writing down the members which are connected to the respective joints. That is, for B it is BA, BC, for C it is CB and CD. And third column is relative stiffness. If you're new to this concept of relative stiffness, don't worry, I'll just show you it in short. I won't explain the whole concept, but I'll tell you how the formulas come. Here B is an intermediate support, and BA and BC are the two members connected. A and C are the end joints and B is the intermediate joint. Alright. So if my A is fixed, then my relative stiffness for member BA is EI by L1. This is the formula. EI by L1, when L1 is the length of member BA. Okay. And for member BC, we call it as far off end. This C is the far end of BC. So if my far end is hinged or it is roller, that is basically my far end is a pin jointed support, then my relative stiffness is 3 by 4 EI by L2. So when my far off end is a fixed support, my relative stiffness is EI by L1. If my far off end is a pin jointed support, my relative stiffness is 3 EI by 4 L2. Yeah, I mean the length of the member. Okay, so now we'll see again. For my BA, my far off end is fixed. Okay, so it is EI by L. BC, again our first primary assumption while solving indeterminate beams are that all the intermediate supports are considered to be fixed. So my C is also fixed. Alright, since it's an intermediate support, therefore BC, the C far off end is fixed. That is the reason relative stiffness is EI by L. Okay, and care is to be taken now that I is changing. Here for these two members the I is same, but for the last member it is 1.5 times I. Okay, so for CB the relative stiffness is, since B is the far off end for member CB and B is fixed since it is an intermediate support, therefore relative stiffness is EI by L. And for CD, I'm sorry, there is a mistake here, I'll just correct it. It's 3 by 4. For CD, since D is the far off end and it is hinged, okay, D is an end joint and it is hinged, so far off end hinged, that is the reason relative stiffness is 3 by 4 EI by L. 3 by 4 EI by L. Okay, so now we write them here. EI by L, so I is not changing, so it is EI by 4. Again for BC it is EI by 4. For CB again it is EI by 4, and for CD it is 3 by 4 E into 1.5 I by L. L is 3. Got it? So in this manner we have to find the relative stiffness. Now total relative stiffness. Total relative stiffness for joint B is the relative stiffness of member BA plus member BC. So if I add these two, I get my total relative stiffness for joint B, which is EI by 2. Okay, and total relative stiffness for joint C is relative stiffness of joint of member CB plus CD. So if I add these two, I get 5 by 8 EI as total relative stiffness of C. What is distribution factor? Distribution factor is basically a relative stiffness divided by total relative stiffness. So for member BA, it is EI by 4 divided by EI by 2. I get it as 0.5. Again for BC it is EI by 4 divided by EI by 2. I get as 0.5. For CB it is EI by 4 divided by 5 by 8 EI. I get as 0.4. And for CD it is 3 by 4 E into 1.5 I by 3 divided by 5 by 8 EI. I get as 0.6. Now we come to rotation factors. The next column, which is a rotation factor, it is basically equal to minus 0.5 into DF. Distribution factor that we found out, it is so rotation factor is equal to minus 0.5 to DF. So I just have to multiply these distribution factors by minus 0.5. I get my rotation factors as minus 0.25, minus 0.25, minus 0.2 and minus 0.3. That's it. So step 2 is completed. We found rotation factors successfully. Step 3, a very important step, which is Carneys box. So here there is a little bit of change. Okay, nothing as much. If you have seen my previous video, here it is fixed end moments. Again, I'll just show you. Here you will have to write fixed end moment of AB Here you will have to write fixed end moment of BA, and at the intermediate supports you have to draw these two boxes. These are called as Carneys boxes. Okay, and these have to be drawn only at the intermediate supports. Since my B and C are intermediate supports, I draw these two boxes there, and outside the boxes I have to write my fixed end moments, whatever I found out here. Okay, so I write it as minus 80, plus 80. For BC it is minus 40, for CB it is plus 40, for DC I'm sorry, for CD it is minus 20, and for DC it is 10. Okay, now the thing is that we cannot have a moment value at pin joint. Okay, pin joints are basically, they cannot carry any moment. Fixed end supports only carry the moments. Pin joints basically have zero moments. Okay, so before starting my iteration process, okay, in Kani's box we do the iteration processes. So before starting the iteration process, what I'll do is I'll just balance this 10 kilonewton meter and I'll make it 0, because I'm balancing this end already. Okay, so what I'll do, there is a 10 kilonewton meter moment. I'll myself add a minus 10 kilonewton meter moment here. Okay, so what happens is summation becomes 0, so there's a 0 moment here. I have balanced this joint, but we have to take care of the minus 10 kilonewton moment that we added. So what happens is that moment is carried off to the next immediate member, next immediate support, and it becomes half. So I just have to multiply minus 10 into 0.5. So here it becomes half, minus 5. Okay, and then we have to add this as well. So as we added this, we got 0. As we add this, we get is minus 25. So this moment is basically what we are going to use. Alright, now let's fill the boxes. This is nothing but summation of my fixed end moments that I have written adjacent to the box. So this is basically minus 40 plus 80. I have to write in middle inside the box. Here also I have to write as minus 25 plus 40, just simple summation. Okay, and here this is 0. So actually what we are going to do is that we are not going to touch this joint now, as we have already balanced it. That was our first job that we did before doing any iterations. Okay, so here we'll write just 0 everywhere. So let's start with our first iteration process. This is equal to summation moment plus latest iteration value of left support, that is 0, plus latest iteration value of right support, that is there is no value. Okay, into the rotation factor of BA. So this is what iteration value of BA. It is very simple, only one formula you have to use everywhere. Summation moment plus left iteration latest iteration value of left support plus latest iteration value of right support. Since A is to the left of B and C is to the right of B, that is the reason left support and right support. Okay, and since there is no value here, it is taken as 0. Into the rotation factor of BC, we get the iteration value of BC. Now we will find iteration value of CB. It is equal to summation moment plus latest iteration value of left support, that now B is to the left of C and the latest iteration value is minus 10. Okay, plus latest iteration value of right support, since D is to the right of C and the latest iteration value is 0, into rotation factor of CB. This is my iteration value of CB. Now I'll find iteration value of CD. It is equal to summation moment plus latest iteration value of left support, that is this, plus latest iteration value of right support, that is 0, into my rotation factor for CD. I get iteration value of CD. Okay, I'll just fix them. Since I'm in Excel, I can take the advantage of copy pasting them. Just a minute. So almost done. Yeah. Although I just copy paste them in Excel, but I'll show you that the formula remains the same. Okay, so this is our first iteration step that is done. We'll go for next iteration. Again, we'll write 0 0 here at the ends. Okay, once you have written that, I can do this in Excel. That is, I can just copy paste it. So basically I'll show you that the formula is remains same, that is summation moment plus latest iteration value of left support, that is 0, plus latest iteration value of right support, that is -1, since this was not there earlier. Okay, so the latest value was -1 into rotation factor of BA. Okay, actually I'll just delete this so that it won't cause any confusion. Okay, now summation moment plus latest iteration value of left support plus latest iteration value of right support into the rotation factor. So I get the iteration value of BC. Now I'll get the iteration value of CB, which is equal to summation moment 15 plus latest iteration value of left support, that is minus 9.75, plus latest iteration value of right support, that is 0, into rotation factor. So into rotation factor, when we multiply it, we get the iteration value of CB as minus 1.05, and now what we do is we find the iteration value of CD, which is equal to summation moment, that is 15, plus latest iteration value of left support, that is minus 9.75, plus latest iteration value of right support, that is 0, into the rotation factor of CD. So we get iteration value of CD. Okay, this is our second iteration step. We have to do these iterations till we get these two values as equal. Okay, you can see here there is very less difference. I mean, there is no difference actually, they are equal. So you have to repeat the iteration process till you get these two values as equal. Okay, so I had to do 1 2 3 4 5 iterations in total to get my last value equal. All right, now final step is finding the final moments. Okay, so what I've done here is I've written all my fixed end moments here, that is MFAB, MFBA, MFBC, MFCB, MFCD. This is the new value. Okay, this value, you don't have to write this value because you have now balanced it and it has become minus 25, and here it has become 0 because you have balanced it. So this is 0. Okay, and here you write all the last iteration values that you got, that is 0, minus 9.37737, minus 9.737, minus 1.0526, minus 1.579, and 0. Your next step would be just to copy all these values and write them again. Very simple, just have to copy them and you have to write them again. That's it. And now next step is to take them across each other. Okay, yeah, so this value comes here equal to this value comes here, this value comes here, this value comes here. Now you won't take this value here because we have already balanced this joint, alright, and we don't have to do anything with this joint now. We have balanced it here, so we won't further take any moments across this. We just have to carry this 0 to this side. Okay, and now just simply add them. This is equal to sum, adding all these values. Okay, Excel. All right, got it. So we just add all these values and write it. Okay, so these are my final moments. You can highlight them if you want. These are my final moments. And as you can see here, this is 60.526, this is minus 60.526, so they have to be equal in magnitude but opposite in nature. Again here, equal in magnitude, opposite in nature, and here it is 0 since we had balanced it earlier. Alright, now what this means is negative sign indicates anti-clockwise movement and positive sign indicates clockwise movements. That is the sign convention that I had taken previously. If you consider a different sign convention, you'll get the answers accordingly. Alright, so we have now successfully analyzed this problem as well, and problem 2 is complete.